Hello everyone, my name is Suyash Gupta, and today I will be presenting our paper, Permissioned Blockchain Through the Looking Glass, Architecture and Implementation Lessons Learned. This work was done along with Sajjad and Mo, and we did it at Exploratory Systems Lab at University of California, Davis. So what is this work all about? This work pertains blockchain. What is blockchain? Blockchain is a linked list of blocks. Each block includes the hash of previous block, and each block includes a set of client transactions. Why should you use blockchain? Well, blockchain dictates a simple philosophy. Why should one person manage all the data? How about we give everyone a right to make decisions? In specific, blockchain talks about three main characteristics. It's about democracy, decentralization, and authentication. And obviously, it gives security. Now, what are the components of a blockchain system? A blockchain system includes replicas, which store data. It includes clients, which send their transactions to the replicas. Further, at the core of any blockchain application is a Byzantine Fault-Tolerant consensus protocol. What this protocol states is that it ensures that all the participating replicas order each transaction in the same manner. Often such a protocol is led by a replica designated as the primary, and all the other replicas act as backups because they follow whatever the instruction primary tells. A blockchain system also includes cryptographic constructs. These constructs include digital signatures, which help replicas to sign their messages, and it also includes collision-resistant hashing. Basically, it allows to create digests. Now, what are the known applications of blockchain? Everyone knows about cryptocurrencies because they're famous, like Bitcoin, Ethereum. Apart from them, there are also emerging blockchain applications like energy trading management, healthcare, waste management, and so on. So why do we all just know about cryptocurrencies? Well, first of all, throughput of existing blockchain applications or these cryptocurrencies are very low, less than 10 transactions per second. And this is one of the reasons why blockchain technology has not been adopted by many different domains. And throughput of existing distributed databases is quite large, which is 1 million transactions per second. And this is the key gap. And for this very reason, blockchain known applications include cryptocurrency. These cryptocurrencies fall under a hood of a set of applications called as permissionless applications. So this brings us to a discussion about permissionless and permission. What are permissionless blockchains? Permissionless blockchains include cryptocurrencies like Bitcoin and Ethereum. What do these applications talk about is that they aim to provide everyone an opportunity to participate. Anyone can participate. It's an open access system. And the key issue with this system is that identity of the replicas need not be known. Now, if the identities of replicas are not known, then they need a protocol which can ensure that there are no malicious attacks. And to do that, they use expensive protocols. One of the famous known protocols is proof of work, which require these replicas to compute complex hashes. And proof of work has been shown to waste a lot of energy. Now, what does proof of work requires? Basically, proof of work requires every replica to find a sort of a hash, and which is very expensive. And the replica which finds this hash fastest wins. Basically, it actually proposes the next block. Now, many replicas would be trying to do that. This means there will be multiple simultaneous proposers, which also means there can be forks in the blockchain. Basically, multiple proposers might propose the next block at the same point of time. And that is a key disadvantage for permissionless blockchain system, because we don't know the exact time when to trust the next block. On the other hand, permission blockchain systems, here the identities of the replicas are known a priori, before even the start of the process, you know which all replicas are participating. And that is why they have been adopted in many applications like blockchain databases and healthcare. And these systems, they do not require any protocol which requires wastage of energy or computation of complex hashes, because the identities are known a priori, and that's why they use traditional BFT protocols like PBFT, ZZY, and SBFT. And these permission blockchain systems are obviously computationally cheap. But if there is low computation, somehow the interaction has to be done. And that interaction is based on communication. And these protocols require high communication, which is often stated as a reason for their low scalability. And it has been seen that even though there is less computation, the throughput of these systems is still very low, which is 10,000 transactions per second. While we saw the traditional distributed databases, they give up to 1 million transactions per second. So there is clearly still a gap. And why does this gap happen? So if you ask anyone, hey, why is a permission blockchain system not performing well? The most cited reason is that the underlying BFT consensus protocol is expensive. And that is what we want to differ at. We want to say that it's not just the BFT protocol which matters, but overall the system design also matters. And to explain our thought process, we ask a very simple question. Can a well-crafted system based on a classical BFT protocol outperform a modern protocol? In specific, in this graph, we show that ResilientDB, our system, outperforms a state-of-the-art permission blockchain system. And this happens when ResilientDB is employing a slow BFT protocol, such as PBFT. Note that PBFT requires 3 phases of communication, and of those 3 phases, 2 of them require O of n squared communication. And the other system, in comparison, uses a fast protocol like ZZY, which only needs 1 phase, and that phase itself is linear. So despite all of this, ResilientDB is still performing. And why does this happen? This happens because ResilientDB employs a system-centric design. It is not just protocol-centric. We're not just aiming the design to be heavy on optimizing the protocol. We're looking at different aspects of the system designing. How can we design a permission blockchain system which can be efficient? And in this graph, we can easily see that even at 32 replicas, ResilientDB is getting 60% more throughput. So it's quite scalable compared to existing systems. So what do we do in this paper? In this paper, we study the best practices existing, and we try to adopt those practices in our ResilientDB system. ResilientDB is open source, and anyone can download and anyone can work with it. And what we have learned throughout this study is that existing permission blockchain systems have overlooked these design principles. And if these design principles are adopted, the system can really become fast. So first step in this study was to dissect existing permission blockchain system and to understand what was going inside them. So first thing we realized is that these existing permission blockchain systems, they have a single threaded monolithic design. What do I mean by that is that these systems have just one thread, and that single thread is running the whole protocol. In each protocol or in each system, there are multiple phases. And if a single thread is supposed to be doing all of those phases, then most of the requests will be just sitting in a backlog, and obviously system performance will be less. Further, one component in any blockchain system is ordering of transactions, and another component is execution. If we're just going to use one thread, which will do both ordering and execution, then we are basically not even separating out these phases. And that is what most of these existing systems are doing. They have single integrated ordering and execution phase. It's easy to separate out these phases and to achieve higher throughput. Further, a lot of these systems just talk about strict ordering. They say that first request has to start, that request has to be ordered, then its execution has to be completed, and then only the next request can start. Well, this whole process is limiting. It is easy to allow multiple requests to be processed out of order and ensure still that the execution happens in order. And that can easily uplift the system's throughput. Moreover, most of the systems are employing off-chain memories. And as soon as you have an off-chain memory, the computation high because there will be latency just to access the data. In this paper, we will study different memory practices which can help in achieving high throughput. Further, a lot of existing systems, they use expensive cryptographic practices. For example, they just use digital signatures, while it is possible to use cheaper message authentication codes, which are not only cheaper, but also give good performance. So here's the ResilientDB architecture. In this ResilientDB architecture, what we want to show here is that it's a layered system. It consists of different layers. There's an execution layer, which actually executes all the transaction. It also has a set of queues, which for different threads to process their messages. There's a storage layer, which basically manages the blockchain and any metadata required. There's a network layer, which basically does the task of exchanging messages between replicas and clients. And there is a secure layer, which basically helps in performing signing and hashing. Further, there's an ordering layer, which helps to run the BFT consensus protocol. To have a look at ResilientDB, let's have a look at this diagram. In this diagram, we show a replica first as a black box. And this replica connects with the network and actually interacts with other replicas and clients. If we remove this black box and try to go deep inside replica, what we will see is that there are some set of input threads which are basically communicating with the network. They're receiving different type of messages. If they receive client requests, then they send those messages to another set of threads which are supposed to batch these requests together. Then, if there are different type of messages required for consensus, like if we just talk about simple PBFT protocol, and in a PBFT protocol, there are messages like prepare, commit, then there's a worker thread which manages these messages. And obviously, while running any consensus protocol, periodically we have to checkpoint the system. We have to see if all the replicas are in the same state or not. So we have a checkpointing thread, which basically creates the checkpoints and manages checkpoints from other replicas. Of course, once these threads perform different tasks, now these messages may have to be communicated outside to different replicas. And for that, we have output threads. Further, they might be required to do some processing, actual execution of the transaction. And for that, we have an execution thread. So this is how ResilientDB's multi-threaded deep pipeline looks like. If you will have a look, instead of using just one thread, we are trying to split the different phases of consensus or the whole blockchain across threads. And that helps us extract more throughput from the system. So, as we are talking about analyzing the system, the key part here is to evaluate it. And while evaluating, in our paper, we ask 11 different questions regarding the factors which affect the performance of a permission blockchain system. Now, to test our system, we employed YCSB, and we used the very simple PBFT protocol for consensus. Now, even though we ask 11 distinct questions in the paper, in this presentation, for brevity, we'll only discuss few of them. The very first question we want to discuss is, what is the effect of pipelining and multi-threading? Can pipelining and multi-threading help ResilientDB to gain higher performance? And to do that, we make ResilientDB use PBFT, a very slow protocol, and we also make it use Ziziva. And what we want to show here is that there will be cases where when ResilientDB is using PBFT, it is still outperforming a system which uses Ziziva. To start with, we have different metrics here. First, we use the symbol E to refer to execution threads and symbol B to refer to batching thread. In this whole figure, we are working with one worker thread and we'll be weighing the number of execution threads and batching threads. For example, when I say PBFT 0E0B, what do I mean here is that we ran the experiment with PBFT and there was 0 execution thread and 0 batching threads. In this specific diagram, the first time when we ran with PBFT having 0 execution thread and 0 batching thread, and Ziziva having 0 execution thread and 0 batching thread. Clearly in this scenario, Ziziva will perform better than PBFT because it is a linear protocol requiring just one phase. But as soon as we gave an extra execution thread, basically as soon as we separated out execution from ordering, we can clearly see that there is a change in performance. In fact, there's already a variant of PBFT which has started performing better than Ziziva's variant in some initial setting. Now, when we go forward and we extend the pipelining, basically, instead of having 0 batching threads, we now have a system where there is one more batching thread. The performance has significantly improved. In specific, this is the PBFT version having one execution thread and one batching thread. And as you can see, it is already performing better than 2 Ziziva versions. Obviously, Ziziva itself will perform when it is given more number of threads. And if we continue further, when we give instead of 1 batching thread, we give 2 batching thread, this version of PBFT wins over all the 3 existing versions. And that is the main insight of this paper. If you have a multi-thread system and you're able to pipeline the phases of consensus, you may not actually require a faster BFT protocol. Basically, the system design should be more system-centric than being a protocol-centric. Now, another of our insight was, how does batching affect the system? There have been some works which have said that batching is not very important. Maybe we can streamline all the requests one after one another. And then there are some works which say about we should have extensive amount of batching. So what we study in this experiment is that what is the optimal batching? Clearly, when we keep on increasing batch sizes from 1 to 1000, there's an obvious increase. But beyond that, suddenly the throughput starts saturating and there's a decrease. Hence, it is important to find the optimal batching size at which the system can perform. Our next insight was regarding the memory. Basically here, we want to discuss what are the effects of off-chain and on-chain memory. In specific, when we stored the whole ledger inside the memory, the system was performing very well. The throughput was very high and the latency was very low. While when we use SQLite for storing the data, obviously the throughput was comparatively less. Next, we wanted to study, is there actually an effect of number of clients? For example, can we just saturate the system by just sending huge number of clients, and will it actually affect the system performance? And that is what we see. Beyond a specific number, for example here, after 32,000 clients, the throughput is almost saturated. While as you keep on increasing the number of clients, the latency keeps on increasing. Why does this happen? Because the more client requests are there in the system, the system becomes loaded, the queues are full, and that increases the latency for processing the request per client. Another insight which we wanted to test was, is there actually some effect of using different cryptographic schemes? Well, to do that, we used 3 different cryptographic schemes. We employed RSA. Another one was 825519 based digital signatures. And then we used a combination of CMAC and 825519. And as you can see, when there are no signatures, the system has the highest throughput. But using digital signatures can lead to very low system throughput and high latency, while using 825519 plus CMAC, basically a combination of asymmetric and symmetric cryptography, could actually be beneficial for system. So even though we don't have as high performance as no signatures, but still there's still a better deal than just by using digital signatures. So to conclude, what we want to say in this paper is that there are several factors that affect the throughput of a blockchain system. Fast consensus does not always imply an efficient blockchain system. In this paper, we show that a well-crafted system-centric permission blockchain system can outperform a protocol-centric design. In specific, we want to show that system designers need to dissect their application to find the performance bottlenecks before they plan to switch to a faster consensus protocol. Here are the references that talk about this work. Thank you.